Let us now look at application of Gauss law. You would recall that in the previous class we already established Gauss law as total flux equal to charge divided by what? Permittivity of free space, where this charge is the charge enclosed by the surface you're trying to treat. It is possible for you to use Gauss law to determine electric field on a surface, beyond a surface, or below the surface. And how do we actually achieve these? All we need to do, it's convenient sometimes to draw what we call the Gaussian surface around the point where the charge, whose electric field we want to determine, is located. We are going to consider hollow cylinder, solid cylinder, and sphere. First, we're starting with hollow cylinder. You can see the board here. This is a hollow cylinder. You can see a blue marker I used in drawing the hollow cylinder. Then I used black marker to superimpose the Gaussian surface on this hollow cylinder. Okay, why did I draw the Gaussian surface on the hollow cylinder so they have the same dimension? It's because look at the charges. The charges are located on the cylinder itself, along its length. Is that okay? So if you are drawing the Gaussian surface, you draw it across the what? The charge themselves, which happen to be on the surface of the hollow cylinder we're trying to analyze here. There are some cases if the charge is outside, say at this point, it means the Gaussian surface you are going to draw will do what? Will be bigger than the outline, the surface itself you are dealing with, because of where the charge is located. If it is below, inside, then you draw the Gaussian surface inside. Is that okay? Okay, now let's focus on these. Because the Gaussian surface lies on the hollow cylinder itself, it means that the radius of the hollow cylinder, which is A, will be equal to the radius of the Gaussian surface, which is what? R. So I'll quickly derive this formula on how to calculate the electric field. Subsequently, for all the surfaces, I'll just give you the formula. They follow the same pattern. First, we want to determine the charge distribution of this. We are going to use lambda to represent it. Lambda is equal to Q over L. We refer to it as charge density per unit length. That is the charge distribution along the length of this cylinder. We call it what? Lambda. From this equation, you see we can make Q subject to the formula, alright? So it means that Q, it implies that Q is equal to lambda times L. Now let us take note of that. Let's call this equation 1. Okay, now we go back to Gauss law. This is Gauss law, that total flux is equal to charge divided by what? Permittivity of free space, which means that from here, from Gauss law, we are going to have that Q is equal to flux times what? Permittivity of free space if you cross multiply. Then in our previous class, we already established the value of this what? Total flux in terms of cyclic integral is equal to this total flux will give you the electric field times cyclic integral of the area of the surface you are dealing with. Okay, now let us multiply by the permittivity of free space as we have there. So that Q from Gauss law for this surface is going to be electric field times permittivity of free space, then cyclic integral of the area of the surface you are dealing with. The surface is a cylinder. The area of a cylinder total, okay, by integration is going to give us 2 pi RL. That's the area of what? A surface. We call it surface area of a cylinder rather. So the surface area of a cylinder is 2 pi RL. 2 pi R, which is the circumference of this circle, times the length. That gives us the surface area of what? Of a cylinder. So let us call this equation 2. You can see that equation 1 and 2 are equal because both of them are defining the charge distribution here. So we are going to equate this and this. If we do that, my E naught, that is electric field times permittivity of free space, times 2 pi RL will now be equal to lambda times what? L. And so you would notice that this L and length, they will cancel out. If the lengths cancel out, what will be left? Let's make E subject to the formula. It will be lambda divided by 2 pi R. Okay, let's say 2 pi E naught times R. Okay? Remember I made this E subject to formula, so you divide both sides by the coefficient of that E, which is this permittivity of free space, 2 pi R. At this point, what we do, we are going to multiply the numerator and denominator by 2. So I will have lambda divided by 2 pi E naught r, then times 2 over 2. I've not committed any error here because mathematically these two can still cancel out. Is that okay? Now, if you do that, you would have 2 lambda divided by 2 times 2 is 4 pi E naught times r. Now, this formula can still be written as 1 over this 4 pi E naught, 1 over 4 pi E naught, then times 2 lambda divided by radius. And we've gotten this formula that we're going to use in calculating the electric field of this hollow cylinder. But take note that radius of the Gaussian surface is equal to the radius of the what? Cylinder itself. Therefore, means that E is equal to 1 over 4 pi E naught times 2 lambda divided by what? A. And we have gotten the equation that we need for the calculation. I will start it. This is the formula you should know. Memorize it for calculation purpose. This A is equal to radius of the cylinder. This lambda is given as charge per unit length. Is that okay? The unit is coulomb per meter in SI units. Of course, you know other terms here. E is the electric field you're trying to determine at this point. Now, let us look at this question on the board. Okay, a straight wire of length 500 meters carries a charge of plus 6.4 times 10 raised to the minus 6 coulombs. Calculate the electric field at a point 200 centimeters from the center of the wire, assuming uniform distribution of charge along the wire. Now, how do we solve this problem? Recall that as a strategy, we need to bring out what we know from the question. The length of the wire was given 500 meters. And then the charge it carries a 6.4 times 10 raised to the minus 6 coulomb. We're told to calculate the electric field, so we don't know electric field at a point. That is the distance. You can use R or A, as the case might be. It's equal to 200 centimeters. You need to convert this to meter by dividing this centimeter value by 100. 200 divided by 100 will give us what? 2 meters. Okay, we have to assume uniform distribution of charge along the wire. So this is the situation of a hollow cylinder having charge distribution along its length. They gave us the length. So electric field formula in that case, recall, is 1 over 4 pi E naught times 2 times lambda, where lambda is the linear charge density per unit length. You know that, divided by what? R. You can use A there, as I said already, to represent radius. Okay. Now, this will be equal to 1 over 4 pi E naught times 2. Now, notice that this lambda has the formula Q over L. Is that not so? So you can substitute for lambda there. That's going to be 2 times Q divided by R. The L is a denominator. So that's the formula we're going to use in solving this problem. Remember that a wire is cylindrical in nature, and that's why we're analyzing this to be a cylinder. Is that okay? Now, if we substitute, we're going to have E to be equal to 1 over 4 pi E naught is a constant whose value is 9 times 10 raised to the power 9. We know that already. Then multiply by 2 times the value of the charge is 6.4 times 10 raised to the power minus 6. And then divide everything by radius, 2 meters, times the length, which is 500 meters. If you work out this, 9 times 2 times 6.4, and then divide by 2 times 500, which will give you 1000. That is 1 times 10 raised to the power 3. You're going to get something 115.2. You know, the unit of electric field is Newton per coulomb, because as a base formula, electric field is actually force over charge. Is that not so? As a base formula. So this is the electric field at a point 200 centimeters from the center of the wire for this problem.